Course 3, Investigation 12. Hopefully this is just a quick video showing what you would do for Investigation 12. I would encourage you to try to do this yourself first because it's pretty step-by-step instructions, and then listen to this video. So what we are doing is proving the Pythagorean theorem here, and I'm just going to start reading. When mathematicians want to demonstrate that a particular idea is true, they construct a proof. Following logical steps, a proof describes how certain given information leads to a certain conclusion. Indeed, virtually all of the structure of math is built on conclusions reached by proof. If you ever go to a college, that mathematics department is going to be basing their classes on proving different theorems. So, one extremely important useful conclusion about our world is that a right triangle, the lengths a and b and the lengths of the hypotenuse are related in the following way. A squared plus b squared equals c squared. This is, of course, the Pythagorean theorem. Mathematicians have constructed hundreds of proofs, literally, to show this. And even James A. Garfield, one of our presidents in America, is credited with proving an original proof for the Pythagorean theorem. In this investigation, we'll develop one of the many proofs of the Pythagorean theorem, work through the exercises as much as you can first, and then watch this video. So the following proof is based on the characteristics of similar triangles. And remember, similar triangles, the corresponding angles are congruent, meaning they're all the same, and that the lengths of corresponding sides are proportional. So same angles, proportional side lengths of those corresponding sides and angles. So the following proof is based on the characteristics of similar triangles. Recall that the corresponding angles of similar triangles are congruent, lengths are proportional. Okay, we've already read that. Sorry to read it again. But number 1, begin by sketching a right triangle. Name the vertices A, B, and C. Okay, so I'll do that down below here. So any right triangle, doesn't matter what those lengths are. We have A, B, and C right here. And we're saying this is my right angle. So we have a right triangle. Okay. So number 2, it's customary to refer to the lengths of the sides of a right triangle by the lowercase form of the letter of the opposite vertex. So along segment AB, write lowercase c, along segment BC, write lowercase a, and along CA, lowercase b. So across from that vertex, so across from C is the hypotenuse, so we put a little c representing that big side length. Across from A, we put a little a, and across from B, we put a b representing that side length. Since this is a generic right triangle, we don't know what the lengths of the sides are. However, it's not necessary to know it in order to show this proof. Next, draw a segment from vertex C across the triangle AB so that the segment is perpendicular to AB, meaning going from this vertex, we're going to draw this line so that this is perpendicular. We are going to call that vertex D. So this vertex right here is D. Point D divides AB into 2 shorter segments. So it's dividing this C value, the side length of that hypotenuse, into 2 different amounts. We have already labeled the distance from A to B as C. Now label the distance from B to D, so just this short segment of this right triangle, we're going to call that X. And the distance from D to A as the rest of C, which if the whole thing is C, and I have taken x out of that, then I must have c minus x left for that segment from A to D. Okay, so check your drawing with the following description, and I'll tell you we have actually set it up correct, so I'll skip that right here. We use this figure and what we know about similar triangles to prove the Pythagorean theorem. Before proceeding with the algebraic proof, we need to be convinced that the 3 triangles are actually similar. One way to prove this is knowing that all of the degree measures are the same within the triangle for those corresponding angles. So number 5, what is the sum of the measures of any 2 of our acute angles in a right triangle? So if I have a right triangle, they are saying these 2 measures here, what are they always going to be? Well, a triangle is always 180 degrees. But I have one of the angle measures as 90. So for these 2 acute angles, that one and that one, they're going to have to add up to 90 degrees. Okay, and you can explain why in your own words of what I just did right here. So if the angle B, so this one right here in our triangle, measures m degrees, then how many degrees is the measure of angle A? Well, I just said that angle A and B always have to add up to 90 degrees. So if I know that angle B is m degrees, angle A must be 90 minus m degrees. So we have A here as 90 minus m. Number 7, if the number of degrees in measure of angle B is m, and the number of degrees in measure of angle A is 90 minus m, then how many degrees are in the measure of these two different ones? So now we're looking at some of these smaller triangles within here. So I'm going to change colors here to show this first one. What I first want is the angle BCD, which means I want this angle right here, BCD. We always go in order to find what angle we're talking about. Well, just like we said before, that's one of our acute angles, meaning that BCD is 90 minus m, because angle B was m degrees. So 90 minus m. Then we're going to change to the other triangle here, the other right triangle that we have inside of this big one. And I want to know what is the angle measure of ACD. So ACD, we're looking at this one right here. Well, if that's one of my acute angles in this right triangle, so I know if angle A up here is 90 minus m, then angle C must have been m degrees. Can we conclude that all three triangles in this figure are similar? And we say yes, and I'll draw out what we mean. So if I have the big one here, A, B, C, then I have determined that that has a 90-degree angle, that A is 90 minus m, and that B is m degrees. And then I have two smaller triangles in here. All right, I'll draw those. So I'll draw this one first, and I'm saying I have D right here, I have C, and I have B. That measure of angle B right here is m degrees. C is 90 minus m. So comparing these two triangles, I would say absolutely those two are the same. Those two are similar because they have the same angle measurements. The last one we need to draw to make sure that all three are similar is this one right here. And we have triangle ACD. We have my right angle with angle D, of course. C came out to be m degrees, and A is 90 minus m. Although it's drawn just slightly different, it is actually similar to my other two triangles. Okay, I just drew it slightly different. Okay, so can we conclude that all three triangles are similar? Yes, because of the angle, angle, angle triangle similarity. Okay, continuing on and kind of finishing up this investigation and truly proving the Pythagorean theorem. Since similar triangles have sides whose measures are proportional, we can write proportions that relate the lengths of the sides of the triangles. Because we are referring to the lengths of the sides, we're going to use those lowercase letters a, b, c, x, and c minus x. Recall that when we began with the largest triangle, triangle ABC, that we divided it into two smaller triangles. We will write two proportions that relate the largest triangle to one of the smaller triangles. So we're going to start with number 9. We're looking at the big triangle ABC and one of the smaller triangles, this one right here, BCD. Okay, so if we are looking at these two similar triangles, we know they are similar. I'm going to start my proportion right here. Starting with my triangle ABC is going to go on the top of my proportion, and BCD is going to go on the bottom of my proportion. And the hypotenuse of each of those, for triangle ABC, I'll do ABC in this blue. So the hypotenuse here has length C, okay, so length C, and we have, I'll do this in purple, triangle BCD, that hypotenuse is length A. Okay, now we're going to look at the legs here, and it asks us to do the corresponding legs. Well, with this, if I'm looking at my big triangle ABC, I would say that this leg right here of A corresponds to the leg of X in our small triangle. Both of those are the small legs of my right triangle, and they correspond. So length A in my ABC corresponds to length X in my triangle BCD. And if you need to, I would encourage you to split them apart so that you can see both of them. So I'll do that right here just really quickly. If I have triangle ABC, I have length C and A, and then I have my small one right here. Let me draw them similar so it's easier to look at. I have this triangle of X. I have this length DC that I don't actually know what it is, and that's okay, we don't need to, and my hypotenuse is A. So we are saying C relates to A just like A relates to X. Okay, so that's my first proportion. C relates to A just like A relates to X. All right, now with my next one, I'm going to be looking at this triangle now. And I'll draw it out separate from here. So we have my 90-degree angle at D, and then I have my, I'll put C up here and A. Okay, so I've just turned it a little bit. So we are looking at from ABC, and we are looking first at my hypotenuse just like we did before. So I'm saying C relates to B, the hypotenuse of this guy. C relates to B just like, well, we want the legs now, the corresponding legs of ACD, which in this case, we are looking, I forgot to label this guy. We are looking at B relates to this side right here. And let's see, I think I drew this a little bit backwards, I'm sorry. This should be switched. Sorry about that. Okay, so, yep, that looks much better. We have C relates to B, those are the two hypotenuse of my right triangle. C relates to B, just like B relates to, sorry about that, C minus X. Those are the corresponding sides. So we have two proportions here. C over A equals A over X, and C over B equals B over C minus X. Take a second to make sure that you know where all of that came from in your triangle so that you can relate those two. And the last part of this is the actual proof. We need to cross multiply the proportions that we found in problems 9 and 10. So we have C over A equals A over X. I'll start with that one. And I'm going to cross multiply, and I see that A squared equals CX. Can't simplify it any more than that. I'm not looking for a particular variable to be simplified, so I'm going to leave it just like that. And then I look at my other one. C over B equals B over C minus X. And I cross multiply. I get B squared, and then I have C times this entire quantity on the bottom here. So C times C is C squared. C times negative X is minus CX. Number 12 said, if you have finished cross multiplying the proportions from problems from 9 and 10, you should see the term CX in each one, and we do, CX and CX. In the first cross product, we see that CX equals A squared, and we do. This means that we can replace CX with A squared in the second product. What we're saying is basically these two CX's in these two equations are the same. So I could replace that CX with this A squared. I'm going to plug it in right there. And I'm going to get something like B squared equals C squared minus A squared. Starting to look familiar. What we're going to do next in 13 says transform the equation you gave for your answer in problem 12 by solving for C squared. So in order to solve for C squared, I want it alone, so I need to get rid of this A squared by adding it. And I get A squared plus B squared equals C squared. And this is the proof. By saying that we have similar triangles here and creating proportions for those corresponding sides, we can then transform those proportions into something that we can then use both of them together, like we did up here, both of them together in order to create our Pythagorean theorem. And that is one of many, many proofs of the Pythagorean theorem. Hopefully you were able to get there on your own, but I hope this investigation helps with your homework and with studying.